All right, here we go with our first lecture here on our special topics. We're going to talk about limits, and our first learning target is to be able to determine the limit of a function at a point using some different techniques. So let's talk about, first of all, well, what is a limit exactly? Let's look at an example of a function, a very common function in calculus, so it'll come up again later. What is the value of f of x of sine of x at x equals 0? So let's first of all just talk about evaluating this function at 0. So f of 0 here, we plug in 0 for x in the top and in the bottom. And if you'll recall from your unit circle, which if you do not remember your unit circle, you need to be studying it ASAP because they do expect you to know this like the back of your hand. You'll be using lots and lots of trig values from the unit circle. So the sine of 0 is the y value at 0 degrees. So at 0 degrees, you're on the x-axis. There is no y value, there is no y value. So that's 0. And then, of course, we have 0 in the denominator. This is something that we call an indeterminate form. 0 over 0 is an indeterminate form. It's TE, an indeterminate form. And that means that the function is going to be undefined at this place. Now, another indeterminate form that you need to be familiar with that'll come up later on down the road is infinity over infinity. We consider that indeterminate. It's not equal to 1 because there are different magnitudes of infinity, so you don't know which one we're talking about here. So you need to know 0 over 0, infinity over infinity are what we call indeterminate forms. So this function is undefined at 0. It has no value when x equals 0. You'll see here that we've got the graph. Let's talk about, here's where the concept of a limit comes into play. If you look at this graph, and I'm going to get up and I'm going to point at it here so you can see what I'm talking about. As we are approaching x equals 0 from the left and the right sides, these arrows here on the graph are showing you that the y values are approaching 1. The y values are approaching a value of 1. It never actually equals 1, but it gets infinitely close to 1. We can also look at a table of values for this function. And you can see from x equals 1, as we get closer to x equals 0 here, x equals 1, 0.5, 0.1, we're getting closer and closer to 0. From the right side, that's what this plus right here means. From the right side, we're getting closer and closer to 0. Look at what the y values are doing. They're getting closer and closer and closer to 1, 0.999. I mean, that's essentially 1. And the exact same behavior happens on the left side. If we start at -1 and we move closer to an x value of 0 on the left side, our y values are getting closer and closer and closer to +1. So that's truly what a limit is. The limit of a function as x approaches c. C for us will always represent a constant. And this capital L here is going to represent the limit of the function. So this is the notation that we use. I always, for whatever reason, I always write the LIM, the abbreviation for limit, in cursive. So that's what it looks like when I write it. It has kind of a underscript there of x with an arrow approaching c. That's not a minus and a greater than sign, that's an arrow. Approaching c, whatever constant we're talking about, of the function f of x equals L. That's the notation that we will use for that. So let's look at some simple limits, and then we'll get a little bit more complicated. Remember, you can pause this at any point in time when you need to be able to take notes. You can rewind it if you missed something that I said. Whatever you need to do, you control this video for yourself. So let's talk about the limit as x approaches 7 of the function 5. A lot of times limits are easier to think about if we have a graph. So let's just sketch a quick graph of the function 5? Well, it's kind of that simple one that you did way back when that you kind of forget. If your function is equal to 5, that means your y values are always equal to 5. That is the function f of x equals 5 or y equals 5. So as our x values are approaching 7 over here, so as we're getting closer and closer to 7 from both directions, what y value are we approaching? Of course, we're approaching 5 because our function is always equal to 5. So that's a really easy question, but they like to throw it in there because they'll do something like this on the AP exam. They'll make it look like this. They'll say, well, what's the limit as x approaches b of 5? And they won't tell you what b is. And one of the answer choices will be not enough information is given, okay? And you may think that that's the answer because they don't tell you what x value you're approaching, but it doesn't matter what x value you're approaching with this function. The limit is always going to be 5 because your y values are always 5 for the function f of x equals 5. Let's look at one that's a little bit more exciting than just a constant function. The limit as x approaches 4 of x. The limit as x approaches 4 of x. So I'm going to do the same thing. I'm going to sketch this function out really quickly. So the limit as we approach 4 of x, don't forget x, y equals x is just that simple line that goes through the origin. It has no y-intercept. Well, its y-intercept is 0. It has a slope of 1. So if we're approaching an x value of 4 here, we are coming at the graph from both directions, and we are approaching a y value of 4. So this is another really easy one that they can ask you about. It doesn't matter what your x value is approaching. We can make it a negative number. It doesn't change the answer. The answer is still, not 4. It's not always 4. It's whatever number you're approaching. So if I say it's approaching negative 11, then the limit is going to be negative 11. If it's approaching, let's say 100, then the limit is going to be equal to 100. It's as simple as that. So here's a very simple theorem. We will have a lot of theorems in this class. You need to kind of write them down. If you want to keep a running list of them, that's fine. They do like to kind of test you on them. You need to know what they say. So here's our first theorem for any constants, c and k. Okay, again, remember, they're just representing constant numbers, 5 and 3. Negative 1 and 7. It doesn't matter. They're just constants. So the limit as x approaches c of k, if your function is a constant, that limit is always going to be equal to that constant. And the limit as x approaches c of x is equal to c. So if your function is x, then the limit is whatever value you are approaching. Okay? Simple as that. All right, let's get to another little more exciting function there. The limit as x approaches 4 of x squared. We can look at the graph, we can look at the table, we can look at a bunch of different things, but it comes down to the fact that if we plug in 4, we find out that we are approaching 4 squared, which is 16. The limit of this is going to be 16. So let me sketch out that graph really quickly, just so we're sure. You got to know what x squared looks like. Okay, x squared goes through the origin. It's just your simple parabola. So if our x value is 4 right here, the question is, what y value are we approaching? We are approaching, and I know my scale's terrible here, but we are approaching a y value of 16. So you see that statement. When f of x is a continuous function, this is the key. It must be a continuous function, then the limit is simply equal to the function value. So if we've got the limit, the question is, what's the limit as x approaches 3 of 5x plus 2? It really is just as simple as plugging 3 into that function there. So this is how we would write it. Right beside the limit, we're going to say equal to. We're plugging in the number, so we don't need the limit notation anymore. It's just equal to 5 times 3 plus 2. Half of the exam is calculator inactive. Half of the exam is calculator inactive. So I encourage you, I know I'm not going to be there right by your side all the time, but as much as possible, practice doing math, doing basic arithmetic, doing basic computations without touching your calculator. I cannot stress it enough. You've got to be able to quickly and efficiently and reliably be able to do these simple math problems to be successful on the exam. So practice, practice, practice without using your calculator. So 5 times 3, of course, is 15, plus 2 is 17. That is the limit of this function as we approach 3. If we were approaching a different y value, obviously the answer would be different. Now, I know that probably sounds like a very obvious statement, but I've had that question before. So it depends on what x value you are approaching. Let's look at example B. The limit as x approaches 0 of 4x squared plus 2x plus 5. Plugging in 0. You probably don't need to show all this work, but I am just for the sake of being explicit right now. Plugging in 0, we've got 4 times 0 squared plus 2 times 0 plus 5. Well, 0 squared is 0. 2 times 0 is 0. So those are 0. So 0 plus 5 is simply 5. Okay, let's look at an example as we're approaching a negative value. The limit as x approaches negative 3 of 5x plus 9. So let's plug in negative 3 into our function here. 5x plus 9 is a linear function, so it's a continuous function. So we can just plug it in. 5 times negative 3 plus 9. 5 times negative 3 is negative 15. Negative 15 plus 9 is negative 6. Negative 6 is our answer there. Okay, so simple linear quadratic functions, no big deal. Let's look at a rational function. They love, and by they, I mean the AP people, love rational functions. They love to use them all over the exam. You really got to know your rational functions. So if you've forgotten this stuff from pre-calc, which hopefully you haven't, but if you have, I'm going to review it as much as I can, and y'all just let me know when you've got questions about it along the way. Let's look at the function 1 over x minus 2. Now to help us out, I went ahead and put the graph of it there so we could visualize it. If you will recall, for rational functions, when the denominator is equal to 0, whatever makes the denominator equal 0, we have a vertical asymptote. So in this case, x minus 2 equals 0, we have a vertical asymptote at x equals 2, which you can see here on my graph. It doesn't have the line plotted out, but you can see that asymptotic behavior there. So that means our function is undefined at x equals 2. The function is undefined at x equals 2. Let's talk about the limit. Let's go back to the graphical perspective of a limit. We follow the graph from the left side. We're trying to see what y value we're headed to. Well, if we follow that, our y values are decreasing a lot. They're headed down towards negative infinity. From the right side, let's follow our graph. Our y values are going up towards positive infinity. In all the other previous examples, our y values have been headed to the same place on the left side and on the right side. In this case, it's not. So here we finally have an example of an undefined UND, or sometimes they will write it out completely on the exam, undefined. That is an undefined limit. As we approach 2 of this function, 1 over x minus 2, our limit is undefined. Let's look at another rational function. Okay, the limit as x approaches 4 of x minus 4 over x squared minus 6x plus 8. Now, you got a choice. you can go ahead and plug in the 4, see what happens. Or you could kind of analyze this as a rational function. I'm going to just go ahead and plug it in because I want to prove a point here. So 4 minus 4 on top, 4 squared minus 6 times 4 plus 8. So in the numerator we have 0. That doesn't mean stop though. We can divide 0 by a constant and still get an answer. Okay, just because there's a 0 involved in our fraction doesn't mean automatically put the brakes on. The denominator is what's more important here. 4 squared is 16, minus 24, plus 8. Here's where the problem's coming up. 16 minus 24 is negative 8, plus 8 is 0. There's that indeterminate form again. Indeterminate. There's that indeterminate form. But remember our example before, we still had a limit when there was an indeterminate form. It's not like example D. It's not undefined. So when we have an indeterminate form, it means we're going to have to do a little bit of manipulation to see if we can fix that indeterminate form. So you know with rational expressions, the way to fix them is to see if we can factor and cancel. So the top is factored. Okay, I'm going to keep my limit notation here because I haven't actually evaluated it yet. The top is what it is. We can factor the bottom, x minus 4 times x minus 2. So we're in luck. The problem, the factor of x minus 4 cancels out. So we are left with the limit as x approaches 4 of 1 over x minus 2. Well, that was the function we were just looking at. So let's look at its graph. As we approach x equals 4, from the left and from the right, we are approaching, we have a y value on this one, and it's 1/2. Obviously, you could also plug this into the function here, 1 over 4 minus 2, and you get 1/2 as the answer. I just wanted to show you graphically and algebraically. One of the big things on the AP exam is being able to represent functions in multiple ways. You got to be familiar with their graph, their symbolic representation. You've got to be able to manipulate tables. You've got to be able to manipulate several different representations of a function. So when you see these functions, you need to start building a mental picture of what they look like, because I promise you it's going to help you out with answering these questions. All right, so I want you to practice with just these simple types of limits. You'll find a worksheet, a PDF of a worksheet there on the haiku page, and I would like for you to start with problems 1 through 16, and then you can move on to the next lecture.